Okay, this is our third lesson on solar energy application. This is a part 2 of solar radiation. I think we should continue one more part for solar radiation in the next session. And today we want to continue the Sun-Earth geometry calculations. So be with me in this lesson. As explained before, this is the main textbook. Whenever any figure is shown in the slides, is taken from this book. Other references will be cited as accurate. In the previous session, we discussed about the Sun-Earth distance, variation of Sun-Earth distance during the year, meaning of solar constant, and its variation during the year, the difference between extraterrestrial and terrestrial solar radiation, the meaning of beam and direct, the beam and diffuse radiation, and how they affect the different solar systems, how they are measured, and a short discussion about solar radiation on tilted surfaces. And the important point last week was about the difference between irradiance and irradiation. I just want to emphasize and ask you to read this one, actually the difference between irradiance and irradiation once more, or even twice if needed, because it's very important. And we looked at some solar radiation resources. Today we want to discuss about the location on Earth and coordinate system, effect of coordinate on our calculation, solar versus standard time, what's the meaning, major parallels of latitudes. We discuss about the declination angle, which is an important parameter, and seasons. We watch together a movie about the seasons, and start to introduce some important angles in solar calculation. So let's start. The first question is, why at all locations are important in solar energy calculation? Why location on Earth is important? Because actually, as you can see in this simple figure, the location on the Earth, where you are on the Earth, actually, for example, if you are here, or here, or here, will affect the sun, the radiation characteristic, both its direction and also the intensity of solar radiation. Also, it will affect the location of the sun, for example. So it's important to know more about the coordinate systems on the Earth. You are familiar with it, but once again I want to review. There may be some questions about that. So the first coordinate system, actually we need two parameters to locate any location on the Earth. The first is latitude and the next is longitude. Latitude, as you can see here, lines of latitude start at 0 degree here at the equator and end at 90 at the north and south poles. Everything north of equator here is known as the northern hemisphere, and everything south of equator is known as the southern hemisphere. In this course we show latitude by phi, as mentioned in our textbook, and as you can see, it's the angular location north of or south of the equator. For north we take it positive or show it with n, and for south we show it by s or minus. As you can see, it varies between minus 90 up to 90. The next parameter, as I explained before, as I noted before, is longitude. Lines of longitude run from pole to pole. This is North Pole and here South Pole, crossing the equator at a right angle. There are 360 degrees of longitude because the Earth is a sphere, and the longitude line of 0 degree is known as the prime meridian, which, as you know, passes from Greenwich in England, and it divides the world into eastern hemisphere and western hemisphere. So if we are, for example, here, for example, like Iran or Iraq, it will be shown by E, and if it is the western part of Greenwich, it is shown by W. In this course, longitude is shown by L. There are two important parameters which we will discuss in the next slides. The first is L with the subscript of LOC. Whenever you see L with the subscript of LOC, it is longitude of the location in question. LOC stands for locations. For example, city, for example, in Germany, Berlin, have its own LOC. But LST is a standard longitude of the country or region. Most of the countries has one standard longitude. In some cases, there may be more than one even. For example, for Iran, standard longitude is 52.5 degrees because we are actually 3.5 ahead of the Greenwich, and each sector, actually the Earth is divided into 24 sections, and if you divide 360 by 24 you will get 15. So if, for example, you are in Iraq and your time is GMT plus 3, so 3 multiplied by 15 gives you 45. So for Iraq, standard longitude is 45 degrees east of Greenwich. So remember this, we will use it later. Then, as you can see, you have maps of latitude and longitude. For example, for any location, you can see the latitude and longitude. For example, if there's a city like, for example, Tikrit, it's maybe 34, maybe 0.5 N, it's latitude, and the longitude is somewhere between 42 and 44. Or, for example, for one location, as an example, for Alpha, you can see that it is somewhere between 29 and it's around 30 N. And if you look for it in Google or by mobile phone, you can take the actual value or exact value. But if you are looking just from the map, you can take it as 30. And the longitude is somewhere between 48 and 50, and the exact value is what you can see here. So the next thing which is important for us as solar engineers is that there are locations on the Earth with the same latitude and locations with the same longitude. Let's give you an example. For example, here you can see that Erbil and Kerala are approximately on the same longitude of 44, but their latitudes is different. For example, this is 36 and this is somewhat more than 32. For cities or locations with the same longitude and different latitudes, for the example shown here, for example, Erbil and Kerala, you can see that sun apparent location is the same. Sun apparent location is the location of the sun in the sky where you see as an observer. For a person who is standing in Kerala and Erbil, they both see the sun at the same location. So we say that sun apparent position or location is the same, but day length is different. So the day length for Erbil and Kerala is different. Which is bigger? It depends on the season. Now come to this example. For example, two cities, Sanjar and the other city here. These two locations have approximately the same latitude of 36, maybe somewhat more, but have different longitude. For locations with the same latitude and different longitudes, like the one you can see here, sun apparent location is different. So people here see the sun in the sky at different position than the people who are here. So the time of sunrise, sunset, and solar noon also for these people are different. But the day length is the same for the location which are situated on the same latitude. Let's give you a numerical example. For example, for two cities in Iran. Consider two cities, one at the north as Gorgan and the other south of Iran, Bandar Lenge, who are approximately the same longitude. Here I wrote cities with the same longitude and different latitude. Okay, if you calculate, there are online tools in the internet, you can check with them. For example, sunrise and sunset for these two cities, you can see that the sunrise in Gorgan is, for example, 5:35, and here it is 6, for example. But and the day length, as you can see, is different for these two cities. You can see, but the sun position or sun apparent position for these two cities, as I explained before, is the same. For example, the solar noon in Gorgan is on, for example, for this special day, is the same as the solar noon. Solar noon is actually the time of Azan, or when the sun is exactly in the middle of the sky. You can see that for both it is the same, but day length is different for these two cities. Okay. Actually, the latitude effect, the main effect of latitude, is on the day length also, and you know that day length is important for us as a solar engineer, because we need to know the length of the day for our solar calculation, with when the sun rises and when the sun sets. Now come to this example, which shows two cities with the same latitude but different longitude. So you can see, for example, here two cities with the same latitude and different longitude. For example, there's Ful at the west of Iran and Birjan at the east of Iran. And if you again calculate the sunrise and day length for these two cities, you can see that the day length for these two cities which have different longitude, is the same. For example, 14, here it is 14, approximately the same. The small difference is because they are not exactly on the same latitude. There may be a small difference. But the sun apparent position in the sky is completely different. You can see that solar noon in the Ful is at this time, but solar noon in Birjan is somewhat before. So this guides us to defining different time base for a solar calculation, and that is solar time in comparison to the local time. Local time is the time which your clock shows, and solar time in some way shows the position of the sun in the sky. There's a relation between solar and standard time, as you can see here. The solar time, as you can see, is the time based on the apparent angular motion of the sun across the sky. With solar noon, the time of the sun crosses the meridian of the observer. It means that the sun is exactly in the middle of the sky, as I show you in the next slide. What's the relation between solar time and a standard time? Actually, by this equation, you can calculate solar time if you have the standard time, or vice versa. By the way, it is the difference between these two times is 4 multiplied by LST. You may remember that LST was the standard longitude of the country or region. For example, for Iraq, it was 45. And LOC, as you may remember, was the longitude of the location in question. For example, you may have a specific city in Iraq, for example, Tikrit, Baghdad, or any other location. For all of them, LST is the same, 45, but LLOC for each location is different. So this parenthesis actually correct the deviation between the longitude of the location in question and a standard longitude of the country or region. The other correction is equation of time. Equation of time actually comes from the Kepler law. You know that the velocity of the Earth in its orbit around the Sun is not constant. In some locations, it goes with a less velocity, and in some location the velocity is higher. So equation of time corrects for this, and if you want to calculate it, there are two ways, as you can see is explained here. The first is the equation 153. Here you can calculate E It is based on B, and if you remember, B was a parameter like the one shown here. And N, if you remember, was the day number starting from the 1st of January. The important note here is that we use solar time in our calculations further on, and so you should be able to convert a standard time to solar time and vice versa. This is very important because all of our calculations are based on solar time. So for example, if it is, for example, 4 o'clock in the afternoon now, it is just the standard time, and you should convert it to solar time for your specific location and then go on for the calculations. E may also be calculated from a figure 151. The figures shown like this, actually, where I did not delete the explanation of the figure, is taken from our textbook. For each time of the year, we can approximately take the value of E on minutes from this figure. For example, if it is June or July, between June and July, you can go up, and then to the left you can take the value of equation of time. Okay, for each country or region in the world, you have a specific time basis, for example CET or AST or others. For Iraq, as you know, Arabia Standard Time or AST is used, which is UTC, Universal Time, plus 3. And as I explained before, the standard meridian or standard longitude of the country is 45. For Iran, it is 52.5. And as I know, you may check it because my data goes, for example, for 1 year back. Iraq does not currently observe daylight saving time. If there is a daylight saving time correction, then you should also correct this for the daylight saving time, which is 1 or 0. Generally in the first half of the year it is taken as 1, and for the second half of the year it is taken as 0. But for Iraq, as I know, it is not used. In addition to the equation I showed you before, there are online tools to convert solar to a standard or vice versa. For example, this is an example of the website. Let me show you the website here. This is the website, Power from the Sun. There are a lot of similar websites, but I think it's good to check. Here you can see a solar time calculator. If you click on the solar time calculator, then you have 2 programs here. The first program is to convert solar to local, and the second is to convert local to solar time. For example, I click on this, and you can see this page. Here you should enter the longitude of the location. For example, I don't know, the location in question may be 45, for example. You should enter here the day number, for example 45. You may remember that day number is the number of the day starting from 1st of January. Time zone, for example, if you are in Iraq, you take it at 3. If you have daylight saving or not, I think for you it is 0 in Iraq. And what is the local or clock time? You can enter the local time either in a 24 or decimal format, or hour minute. For example, if I enter it as, for example, this and this, then calculate the result. Here the solar time is shown based on the local time or a standard time which you entered here. So there are online tools that you can calculate or convert solar to local or vice versa. Just once more, I want to emphasize that solar noon is actually the time of day when the sun is at its highest position in the sky, and it's called solar noon. Here, if you are here and this is the sun, solar noon is the time of the day when the sun is at its highest location, or zohr as we say. You know that the time between sunrise and solar noon is equal to the time between solar noon and sunset. This is a homework for you. For example, for 19th this time shown here for Baghdad. Calculate the time of solar noon and check it with other available data, because you know that solar noon is the time of Azan, and you can check it. If there is any difference, explain about that. And at 10 o'clock in the same city in the morning, the same day, what will be the solar time? And these are the rules that you should follow when you are sending your answer to me. The next parameter of importance is the hour angle. Actually, hour angle, as you can see, is the angular displacement of the sun east or west of the local meridian due to the rotation of the Earth on its axis at 15 degrees per hour. Actually, and we take morning negative, afternoon positive, and at the solar noon, as you can see here, please note that this is solar time. This is not a standard time, because at 12 o'clock the sun may not be in the center or highest position. These are solar time actually. So for solar noon, you can see that our angle we take 0, morning negative, and afternoon positive. And for each hour, as you can see, for example, from 12 up to 1 o'clock in the afternoon, the sun position changes 15 degrees. So instead of, for example, saying that it is 11 o'clock in the morning, you can say that the hour angle is minus 15. And if you hear that the hour angle is minus 15, the meaning is that we are 15 degrees before the solar noon, and the meaning is that it is 11 o'clock. You can calculate the hour angle if you have the solar time, or you can calculate the solar time if you have the hour angle by this formula, which is quite simple. Okay, the next important definition is the parallels of latitudes. Actually, there are a lot of parallels to the latitude, but some are important, as you can see here. There are 7 parallels of importance, as you can see in this picture. The first is equator. We discussed about that, but there are some more. The next is Tropic of Cancer, as you can see here, or Ras Saratan, Arctic Circle, Tropic of Capricorn, and Antarctic Circle. Let's have a look at the definition. The equator, as you know, is a line that divides, a plane actually, that divides the Earth into northern and southern hemisphere. It marks the location of 0-degree latitude. Okay, we discussed about that. The next is Tropic of Cancer. The exact latitude is not fixed, but it is approximately 23 in the north of equator. And if you draw a line, for example, to show the location, you can see that it is somewhere here. So, for example, for Iran and Iraq, both are above the Tropic of Cancer. You can see that it passes, for example, from the middle of the India, and in some places here in north of Africa and other. Okay, so for us, we are above the Tropic of Cancer, and actually we are below the Arctic Circle, both for Iran and Iraq. The interesting point for Tropic of Cancer is that the summer solstice, actually some days back, which occur on either 20th or 21st of June each year. For this year, 2021, it was 21st of June, marks the day on which the sun shines vertically over this parallel. So, on 21st of June this year, any location which is on this line, which is the Tropic of Cancer, at solar noon, the sun is exactly overhead of the observer. So if a person stays in these lines, okay, in this line, anywhere in this line on the Earth, and it is solar noon, not 12 o'clock, okay, it's solar noon. It may be different with the solar noon, with 12 o'clock, and see the overhead, he or she sees the sun just overhead. The next parallel is Tropic of Capricorn, as you can see here. It is in the southern hemisphere, the same figure as Tropic of Cancer. And the same explanation here applies for winter solstice or Tropic of Capricorn. The winter solstice, which occurs on either December 21st or 22nd each year, marks the day on which the sun shines vertically over this line. Okay. And there are also two circles, as you can see here, the Arctic Circle and Antarctic Circle. The next definition is declination angle, or Zawiya inhiraf as we say. You know that the Earth axis have an angle or declination of 23.45 degrees, as you can see here in this picture. And actually this is the reason for seasons, and that is very important for us in our solar calculations. To calculate declination angle, which is shown by delta in this course, there is a formula, but let's first have its definition. It's the angular position of the sun at solar noon, okay, with respect to the plane of the equator. The angular position of the sun at solar noon with respect to the equator. If you want this, for example, simple explanation, you can say, for example, it is the angle between the line which connects the center of the sun to the center of the earth. The figure is not on a scale. With the equatorial plane, okay? You can see here the definition. The angle between equatorial plane and the sun ray. This is also a correct explanation. You can use either this or this explanation or definition. What's the formula for calculation of delta? This is the formula 23.45 sine of these parentheses, and again in this parentheses n is the day number, which starts on it starts with 1 on the 1st of January. There are actually specific values for delta which worth of remembering. On equinoxes, we have two equinoxes actually, a spring equinox which occurs on 21st of March and September 23. At these 2 days delta is 0, so the declination angle for these 2 days is 0. And for the summer solstice, which is on 21st of June or 20th of June, it is 23.45, and for the winter solstice it is 23.45 with a minus sign. So you can see that for half of the year the value is negative, and for half of the year its value is positive. And as an exercise, you are asked to calculate the declination angle for 27th of January. So if you want to calculate this, what you should take n, think about that. Correct, you should take n as 27 and then put n in this equation, and you can calculate delta for this specific day. Okay, the next very interesting point is seasons, and we want to know the reason for seasons and the effect it has on solar calculation. There's a very good video for that. I put it here, the link to the video, and I want to ask you kindly to see this video. We can see it together because as I want to be sure that you will see it. So it is 5 minutes, as you can see. It's uploaded on 2007. It's somewhat old, but the explanation is still new and a lot of views you can see here. I ask you kindly to put enough time, 5 minutes, around 6 minutes, to see the video. So I also see the video with you. See you 6 minutes later, okay?
The axis of the Earth is an imaginary line on which the Earth rotates. It links up the two poles. Both the axis and the Earth are tilted at an angle of 23.5 degrees during a revolution. The tilting of the axis results in direct sunlight falling on different different places during different seasons. This causes variations in the duration of days, nights, and seasons. Relationship between the location of the overhead sun and the seasons. Similarly, the revolution of the Earth and the tilting of the axis results in different angle of the sun during different periods. When the sun is directly overhead, we call this the overhead sun. At this time, the Earth's surface and the midday sun forms a 90-degree angle. Different locations of the overhead sun results in variations in the amount of solar radiation received in different areas and at different periods. Spring equinox on the 21st or 22nd of March. The overhead sun is over the equator. The equator receives the largest amount of solar radiation. At this time, the northern hemisphere is in the spring equinox, while the southern hemisphere is in the autumn equinox. The angle of the sun decreases towards the poles. On this day, the two hemispheres receive a similar amount of solar radiation, and the length of day and night is the same at all places on the Earth. After this day, it is spring in the northern hemisphere, where the day is longer than the night. In the southern hemisphere, it becomes autumn, when the day is shorter than the night. Summer solstice. On the 21st or 22nd of June, the overhead sun is over the Tropic of Cancer. It receives the largest amount of solar radiation. At this time, the northern hemisphere is in the summer solstice, while the southern hemisphere is in the winter solstice. The angle of the sun decreases towards the poles. On this day, the length of daytime of the northern hemisphere is the longest in the year, while that of the southern hemisphere is the shortest in the year. Besides, there are 24 hours of daylight at the Arctic Circle and 24 hours of darkness at the Antarctic Circle. Autumn equinox. On the 22nd or 23rd of September, the overhead sun is over the equator again. The equator receives the largest amount of solar radiation. On this day, the northern hemisphere is in the autumn equinox, while the southern hemisphere is in the spring equinox. The angle of the sun decreases towards the poles. On this day, the two hemispheres receive a similar amount of solar radiation, and the length of day and night is the same at all places on the Earth. After this day, it is autumn in the northern hemisphere, where the day is shorter than the night. In the southern hemisphere, it becomes spring, when the day is longer than the night. Winter solstice. On the 21st and 22nd of December, the overhead sun is over the Tropic of Capricorn. It receives the largest amount of solar radiation. On this day, the northern hemisphere is in the winter solstice, while the southern hemisphere is in the summer solstice. The angle of the sun decreases towards the poles. On this day, the length of daytime in the northern hemisphere is the shortest in the year, while that of the southern hemisphere is the longest in the year. There are 24 hours of darkness at the Arctic Circle and 24 hours of daylight at the Antarctic Circle.
Okay, I hope you enjoyed the video, because actually I think it's the best video explaining the situation, and I ask you to watch it more than once, because it worth it. Okay, so based on what you saw in the video, watching the video, you understood that the path of the sun, apparent path of the sun in the sky for different times of the year is different. For example, you have the highest path on summer solstice, which is 21st of June, for example, 20 or 21st of June, and the lowest path is on December 21st. The other thing is that the day length in the summer, for example, in the first half of the year is more than 12 days, 12 hours. And the other important point is that the sun rises not exactly at the east, but for example, somewhere between east and north, or northeast. And in the same way, it sets actually in northwest. And in the second half of the year, the day length is less than 12 hours, and as you can see, the sun again does not start exactly on east, it starts somewhere between east and south, or southeast, and the same for sunset. And not drawn here, but you can imagine that on equinoxes, which is 21st of March, and the same on September, the sun starts or rises exactly on the east, and the sunset is exactly on the west, and the day length is 12 hours. So it was very important, and I kindly ask you to watch it again. Coming to the next explanation, to explain 4 very important angles, which are important angles in solar calculation. Suppose that this is the solar collector or solar module, this line, this plane, okay, and this is sun. You need 2 angles to describe the position of the sun, and also 2 angles are needed to describe the position of the collector or module, or solar surface actually. The 2 angles which are needed to describe the position of the surface are named as solar surface tilt or slope angle and surface azimuth angle. And the 2 angles which are used to describe the sun position are solar altitude angle, or you may use zenith angle, and solar azimuth angle. So you have solar azimuth angle, surface azimuth angle. You have surface tilt, you have solar altitude angle. Okay, let's start first with surface tilt or slope angle. You can see here actually beta, or which we show what beta in this course, is the angle between the plane, the solar module or collector, and the horizontal. We show slope or tilt angle with beta in this book or course, and it is the angle between the plane of the surface in question, which may be a module or collector, and the horizontal. Means that okay, there may be downward facing component, but it is not usable actually or useful for us. In actual situation, actually the surface tilt angle may be somewhere between 0 and 90. is there an optimum angle? Because the first thing when you want to install the solar collector or solar module is at what angle I should install the panel, okay? Is there any optimum tilt angle? Tell it frankly, if you have no other data, you can take the latitude of the location in question as an approximate value, okay? Which works for you for spring and fall. But if you are using the device, the solar module or collector in the winter, it may be best to change the slope angle 15 degrees in comparison to the latitude. It means that add 15 to latitude. And if you want the system to work in summer, for example, if you have a solar cooling system which is needed in summer, then the best angle may be the latitude minus 15. But actually the story is somewhat more complex than these simple rules. We did some research on this topic. Actually, you may see or check for these papers. The first is the optimum tilt angle for flat plate solar collectors in Iran. It is published in Journal of Renewable and Sustainable Energy, and we provided a map for optimum tilt angle in different locations of Iran. And as you can see, even for locations with the same latitude, the angle may be different. And what's the reason? Because we told that it is dependent on the latitude of the location. But you can see here there are locations with the same latitude but different slope or tilt angle. You may refer to the paper to this paper to know more about it. In the same way, we did another work for Abu Dhabi in United Arab Emirates. For optimum tilt and also optimum orientation of solar surfaces in Abu Dhabi, and there are graphs like the one you can see here, and you can see that there is optimum tilt angle, but this line, like the one we can see here, is the optimum tilt angle. You can see that it is somewhere, for example, here, which you receive the maximum annual global radiation. But one important point which we'll discuss in the next slide is the effect of orientation. And you can see here, if the orientation of the panel is not towards south, then the optimum tilt angle may be different, and it's also an interesting topic to discuss. I can only ask you to refer to the paper if you want to know more about that. The interesting point here is that I just did it today. And you can see that just since the beginning of 2021 till 24th of this month, you can see that there are around near 1,500 papers about the optimum tilt angle. So this is not this is an open problem yet, and you can see, for example, optimizing the solar PV tilt angle to maximize the power output. This is determination of optimum tilt angle for solar collector and evaluation of the position of existing building. You know, there are a lot of research going on considering different aspects of optimum tilt angle. So while the simple rule is this as you can see here in this slide, but there are a lot of complexities actually, and if you are interested, you can do your final thesis also on this topic. You may use the optimum tilt angle with the commercial softwares also. For example, you can see here a screenshot from PVSys, which is a solar PV system design software. There are different ones, we will discuss about them later, for example PVSol, Polyson and others. This is a screenshot from the PVSys, and you can see that for calculation of the optimum tilt angle, there was a box which shows what you want to do. Do you want to, for example, maximize the solar yield in the whole year, in summer, in winter, or selected months? And it depends also on the type of system. For example, if your system, PV system, is a grid-connected system, then the story may be different from the standalone or off-grid system. Or if there is a pumping system, the story may be different. Another interesting topic is the effect of type of, if you have a solar heating collector or thermal collector, then, and it is, for example, of natural circulation or thermosiphon type, the effect of inclination angle on this thermosiphon flow circulation may be also important. These are all topics which you may do research on that. Online tools may be also used to determine the optimum tilt angle. You may remember this website, Global Solar Atlas, and if you you point, for example, a specific location. For example, I entered Abu Dhabi in the United Arab Emirates, and you can see here, in addition to other data which we discussed before in lesson 2, you can see here the optimum tilt of the PV modules. The next important angle is the surface azimuth angle, and you can see here this angle. Surface azimuth angle is shown in this book by gamma, and you should differentiate between gamma and gamma with the subscript S, because gamma S is the solar azimuth angle. So whenever you see gamma, it is the surface azimuth angle, which shows the direction of the solar collector or solar module with respect to the south. And if the collectors or panels are installed directly toward the south, then the angle here you can see that it is towards south, and the angle will be 0. Similar to the hour angle, we take morning as negative and afternoon as positive. So if we are here, for example, somewhere between east and south, this means that we are facing toward southeast, and in this case we take it as negative. Okay, just one important point here is that you can see that it is shown that solar azimuth is 180, while I told that the angle when the solar surfaces are towards south, you should take it at 0. As I wrote here, note to the reference direction for 0 azimuth, because in some references or books north is taken as 0, then south will be 180. But in this book, or in our course, we will take south as 0. So if the panels are towards south, then the azimuth or surface azimuth will be 0. Actually, there is no difference, but you should be taking care of it. Similar to the slope angle, there are a lot of complexities behind that, because if you want a simple rule, face the panels or collectors toward the south, but there may be some more complexities behind. For example, what's the effect of off-south surface azimuth angle? You can see here that if, for this graph, this one, is the solar production or yield of panel facing south. You can see that, for example, this is the output. But if you take you for example face the panel southwest, okay, then the production will be different, and you can see that the peak time will be shifted toward afternoon. In some cases, off-south installation may be done to match with the consumption or need. Or in some cases, it may be difficult to exactly place the panel towards south. For example, this, as you can see, is a solar water heater, and you can see such a complex structure is needed just to place the panel toward the south. Anyone may not be desired to do such a complex structure. Or in some cases, roofs may not be directly towards south. For example, this roof may be towards southwest, for example. What you should do, either you should forget installing the panels, or you may put them and neglect some yield. Actually, you will lose some part of the yield. It's important to calculate how much you will lose, okay? And then you or the owner may decide to place the panels or not. Another important point is how to find south. You know that there are a lot of ways to find south, and with that advance of mobile phones, advancing mobile phones, progressing mobile phones, it's also possible to use them also to find south. But one point you should consider or pay attention when finding south. There are two south actually, or two north in the same way: true north or south pole, and magnetic north or magnetic south. And you should take care of the difference between the two. While the difference is not so much, but there are graphs like the one you can see here. The graph also varies during year to year, but you can see here an approximate value, and the lines you can see here are the lines of the correction which is needed for the difference between the magnetic south, which the compass shows, and the true south. Please note that we should face the panel toward the true south, okay? Not the magnetic south which the compass shows. How you can calculate: either you can use the maps, or you may use the online tools like the one you can see here. You can go to this website, the website I shown here, and enter your location, and it gives you the correction which is needed, or the magnetic declination as they will call it, to correct the compass reading to find the true south or true north. There are also apps which may correct for that. Just one thing I wanted to mention here, and it's important because generally mobile phones have this capability. Just remember that whenever you want to use your mobile phone compass, go to the setting of the compass and put it on true north or true south if it is not so, because the default value, you should check what is the default value. If the default value is true north or south, then it's okay, but if the default value is the magnetic north or south, then you should change it to the true north and true south, and then use it for facing your solar modules or solar panels. Okay, this is the end of lesson 3. In the next week we will continue the topic of solar